How are you? I hope you all are well. Today in this video, I am going to explain black body radiation. You might have observed sometimes blacksmiths they heat some metal pieces, especially the iron. For example, you are supplying heat to a piece of iron. What happens? Its temperature will increase. At the same time, it became the red color. Whenever you are continuing to supply heat for the temperature increasing, again it is appearing yellow color. If you continue again, temperature increasing, again it is becoming white color. That means the iron rod, what the blacksmith is heating, at first you observe red color, thereafter yellow color, thereafter white color. What is the reason behind this change of color? To understand the reason behind change of color, we have to learn Wien's displacement law. Wien's displacement law. But this Wien's displacement law is associated with the black body. So at first we have to learn what is black body. Thereafter I shall explain the Wien's displacement law. So what do you mean by black body? You might have listened this word several times. In fact, theoretically, it is a perfectly black. Perfectly black in the sense, see here, this is a substance. Suppose you know that when radiations of different wavelengths incident on a substance, there may be absorption. When the absorption takes place, if the temperature of the substance less than the temperature of the surrounding, then the substance absorbs the heat energy. But once its temperature become more than the atmospheric temperature, it starts emitting. That means absorption is there, emission is there. Some cases the body also transmit, means you can say transmission is also possible. But here we are not discussing about the transmission. Here we are going to discuss about the absorption and emission, because it is the matter of a black body. So what is that black body? How it is? That means it is a substance which can absorb maximum amount of radiation, maximum amount of electromagnetic radiation. That means, for example, an ideal black body is lamp black, or you can say it is a carbon black. Lamp black, in my childhood, My mother used to prepare some black. How? By placing one lamp. Earlier we also used the kerosene lamp. During that burning of the lamp, some smoke gathered on the surface of the glass or on the top surface of the lamp. That is an example of a lamp black. My mother also used to prepare black for using in my eye. She will keep the deepam, or that is the lamp. Over that lamp will keep one pot filled with water. She will keep it for 4 to 5 hours or 6 hours. Bottom of the container will be covered with a black substance, sooty substances. That is the lamp black. So, either you can say lamp black or carbon black. These are the ideal black body example which can absorb maximum amount of electromagnetic radiation. You can say it can absorb more than 99% of the radiations. These type of objects are called the black body. Our sun is also example of a nearly a black body. Why I am telling sun is nearly a black body? Because black body is a substance which can absorb as well as which can emit maximum amount of radiations. So, the absorption and emission, it may take simultaneously, it does not matter. I said that when the temperature of the substance less than the surrounding or atmosphere, that time the substance receive the heat energy. At the same time, when the temperature of the substance becomes more than the immediate surrounding, the substance starts to emit. Absorption and emission may take place at a time, there is no doubt. See here. So, a black body is perfectly black or ideal black body. I said lamp black is an example which can absorb maximum amount of radiations. So, I said that this is a substance. When the radiations are coming, those radiations having the different wavelengths, having different amount of energy. At first it absorb, thereafter it emit, depending upon the temperature. The substance temperature is less, it will absorb from the surrounding. Substance temperature is more, it will release the heat to the surrounding. So, this is about the information regarding the black body. Now, let us come to the point of Wien's displacement. See here. Suppose this is a black body. I supplied the heat. So, when its temperature became more than the surrounding air, it started emitting the energy. That energy may be in the form of light, may be in the form of heat. Suppose the light ray came from it. If I place one prism, already we know that when a white light passes through a prism, the prism disperses the white light into its 7 component colors. Suppose this is a white light ray coming from this substance after heating. If this light ray passes through this prism, what happens? The ray starts bending. Suppose these are the rays, because we know that when light ray passes through prism, it split into its component colors. That colors, you know, it is in a order like violet, indigo, blue, green, yellow, orange, red. 7 colors. 7 color is nothing but a light of a fixed wavelength. That means it has 7 types of a wavelength. Among these colors, the violet deviated maximum because its wavelength is less. Red deviated least, its wavelength is maximum. So those radiation's wavelengths are more, the bending is less, wavelength less, bending is more. That one you have studied in the earlier classes. Now listen carefully. Suppose I shall take one detector. Its work is to detect the intensity of the wave, to detect the energy, or you can say to measure the wavelength of the radiations which coming after the dispersion. So I have taken one detector. Suppose I place the detector here. So detector will detect the wavelength, the intensity of light, or the energy associated with the intensity of the light. Suppose if I move this detector from red to violet, that means I can get information about the wavelength, about the energy associated with the wavelength. So if I plot a graph between wavelength and energy. So in the x-axis I have taken wavelength, whereas y-axis I have taken the energy. The detector will find the wavelength as well as energy associated with the intensity of the light. So suppose now during the supply of heat reached at the temperature T1. At the temperature T1, I found the energy, I found the wavelength associated with that waves. So if I plot a graph, for example, this is the wavelength, this is the energy. That means I shall get this point. Okay. Similarly, if I come from red to violet, I shall find that its wavelengths are decreasing. That means in place of here, suppose the wavelength is here. So if I take the wavelength in the x-axis, energy in the y-axis, I shall find a graph like this. Suppose the graph is like this. Now, see, this is the point where the energy is maximum. So, I can mention this is the lambda m. Lambda m stands for wavelength associated with the maximum energy. Here lambda m, this is the wavelength correspond to maximum energy. That means this is maximum energy wala wavelength. Lambda m stands for maximum energy. This is not the maximum wavelength. From here to here I am coming. Wavelength is decreasing, but the energy height is increasing. When the wavelength is decreasing, energy height is increasing. When wavelength is decreasing, that time what about the temperature? Okay, suppose in this case the temperature is T1. I got this graph. Now I shall change the temperature. Some different amount of heat will be supplied. Suppose the temperature increase to T2 in place of T1, T2. Then this graph will be changed. Now the graph is like this. Suppose the graph is like this. Then what happened? Now the maximum energy came here. Okay? This is the lambda m. That means the wavelength associated with the maximum energy. When the energy is increasing, the height of the energy is increasing, that time wavelength is decreasing. I have taken x-axis wavelength. I started from red. I reached at the violet. The graph became like that. Similarly, suppose this is the temperature T2. If I again change the temperature, I shall get the graph like this. That means, say, you can say this is the maximum height. It represents the wavelength associated with the maximum energy. Wavelength correspond to maximum energy. Wavelength is decreasing. Height of the energy increasing. That means amount of energy is increasing. So, what? Suppose this is the case of the T3. But in all these cases, if I take the product of this temperature and maximum energy wala wavelength and temperature, suppose the temperature T, I shall get one constant term. That constant is called Wien's constant. That constant is called the Wien's constant, or I can say that this law is called Wien's displacement law. This is the displacement. Displacement is maximum when the wavelength is minimum. That means wavelength is decreasing, displacement is increasing. This is called Wien's displacement law. Now I can write it as, see here, T is equal to constant upon lambda m. So I can say that Wien's law states that the wavelength correspond to maximum energy. I can write that this Wien's law. Wien's displacement law states that the wavelength correspond to maximum energy is inversely proportional to temperature in Kelvin. So here wavelength correspond to maximum energy is inversely proportional to temperature in Kelvin, and this Wien's constant, it has a value. Its value is 2.9 into 10 to the power minus 3. So here lambda m wavelength, that is in meter, temperature in Kelvin. So the constant value is 2.9 into 10 to the power minus 3 meter Kelvin. Now suppose in case of a celestial bodies like the sun, for example our sun, if you know its lambda m, that means maximum energy wala wavelength, if we know, easily we can find the temperature of its surface. For example, in case of the sun, in case of solar energy or sun, lambda m is equal to 4753 angstrom. That means I want to say that if we know the value of this lambda m, easily we can find the temperature. That means temperature of the surface of the earth is equal to 2.9 into 10 to the power minus 3 upon 4753 angstrom. So if you calculate, you get 6060 Kelvin. That means the surface temperature of sun is 6060 Kelvin. Not only the sun, in case of any celestial bodies like other stars, from where the radiations are coming, if you know its lambda m, easily we can calculate its surface temperature. So children, don't forget to press the like or dislike button with subscription. If you want to continue the learning systematically, then definitely subscribe. I hope that this video will be shared. So in the next class, I shall explain about the Stephen Boltzmann law. Until then, bye.